because at the beginning of the semester, I couldn't get one set up, and then I finally figured it out, and then the internet went all weird on me.
No, that's what happens when everyone's on it, right?
Well, and then campus, every parking spot was taken for like way more than usual, and
Oh,
especially
really?
for like at 9 o'clock at night. I think I found like two parking lots that had some spaces empty, and that's not really, yeah, it was
No.
insane.
Do you have classes on campus and online?
Yeah, well, I have two classes on campus and then two classes online. So it's kind of a good mix for me at least.
Oh, that's nice.
Like that way I get a little bit of flexibility, but I still have to go on campus because that keeps me a little more focused.
Yeah, I get that.
I'm like, I need something to remind me that I actually have classes online.
That you have homework to do.
Pretty much. I'm not too proud to admit that.
I think that's probably human nature, right?
Figure if you know what works for you, you should probably roll with it, you know?
Yeah, exactly. Cool. So, an attempt to play this video, I think.
Sounds good.
So now that we've spent some time thinking about what a differential equation is and even visualizing solutions to a differential equation using things like slope fields, let's start seeing if we can actually solve equations. And as we'll see, different types of differential equations might require different techniques, and some of them we might not be able to solve at all using analytic techniques. We'd have to resort to numeric techniques to estimate the solutions. But let's go to what I would argue is the simplest form of differential equation to solve, and that's what's called a separable differential equation. And we will see in a second why it is called a separable differential equation. So let's say that we have the derivative of y with respect to x is equal to negative x over y e to the x squared. So we have this differential equation, and we want to find the particular solution that goes through the point 0, comma 1. And I encourage you to pause this video, and I'll give you a hint. If you can, on one side of this equation, through algebra, separate out the y's and the dy's, and on the other side, have all of the x's and dx's, and then integrate, perhaps you can find the particular solution to this differential equation that contains this point. Now, if you can't do it, don't worry, because we're about to work through it. So as I said, let's use a little bit of algebra to get all the y's and dy's on one side and all the x's and dx's on the other side. So one way to, let's say I want to get all the y's and dy's on the left-hand side and all the x's and dx's on the right-hand side. Well, I can multiply both sides times y. So I can multiply both sides times y. That has the effect of putting the y's on the left-hand side. And then I can multiply both sides times dx. I can multiply both sides times dx. And we kind of you can treat these differentials as you would treat a variable when you're manipulating it to essentially separate out the variables. And so this will cancel with that. And so we are left with y dy is equal to negative x. Actually, let me write it this way. Let me write it as negative x e, actually I might put a little more space. So negative x e to the negative x squared dx. Now, why is this interesting? Because we can integrate both sides. And now this also highlights why we call this separable. You won't be able to do this with every differential equation. You won't be able to algebraically separate the y's and dy's on one side and the x's and dx's on the other side. But this one we were able to. And so that's why this is called a separable differential equation. Differential equation. And it's usually the first technique that you should try. Hey, can I separate the y's and the x's? And as I said, this is not going to be true of many, if not most, differential equations. But now that we did this, we can integrate both sides. So let's do that. So I'll find a nice color to integrate with. So I'm going to integrate both sides. Now, if you integrate the left-hand side, what do you get? You get, and remember, we're integrating with respect to y here. So this is going to be y squared over 2. And we could put some constant there. I could call that plus c1. And if you're integrating now, that's going to be equal to, now the right-hand side, we're integrating with respect to x. And let's see, you could do u substitution, or you could recognize that, look, the derivative of negative x squared is going to be negative 2x. So if that was a 2 there, and if you don't want to change the value of the integral, you put the 1/2 right over there. And so now you could either do u substitution explicitly, or you could do it in your head, where you said u is equal to negative x squared, and then du will be negative 2x dx, or you can do this in your head at this point. So I have something and its derivative, so I really could just integrate with respect to that something, with respect to that u. So this is going to be 1/2, this 1/2 right over here. The antiderivative of this is e to the negative x squared, and then of course I might have some other constant. I'll just call that c2. And once again, if this part over here, what I just did, seems strange, the u substitution, you might want to review that piece. Now, what can I do here? Well, I have a constant on the left-hand side. It's an arbitrary constant. We don't know what it is. I haven't used this initial condition yet, we could call it. So let me just subtract c1 from both sides. So if I just subtract c1 from both sides, I have an arbitrary, so this is cancel, and I have c2. So this is c1. So these are going to cancel. And c2 minus c1, these are both constants, arbitrary constants. We don't know what they are yet. And so we could just rewrite this as, on the left-hand side, we have y squared over 2 is equal to, on the right-hand side, I'll write 1/2 e, let me write that in blue just because I wrote it in blue before, 1/2 e to the negative x squared. And I'll just say c2 minus c1, let's just call that c. So if you take the sum of those two things, let's just call that c. And so now this is kind of a general solution. We don't know what this constant is, and we haven't explicitly solved for y yet, but even in this form, we can now find a particular solution using this initial condition. Let me separate it out. This wasn't part of this original expression right over here, but using this initial condition. So it tells us when x is 0, y needs to be equal to 1. So we would have 1 squared, which is just 1, over 2 is equal to 1/2 e to the negative 0 squared. Well, that's just going to be, e to the 0 is just 1. So it's going to be 1/2 plus c. And just like that, we're able to figure out, if you subtract 1/2 from both sides, c is equal to 0. So the relationship between y and x that goes through this point, we could just set c is equal to 0. So that's equal to 0. That's 0 right over there. And so we are left with y squared over 2 is equal to e to the negative x squared over 2. Now we can multiply both sides by 2, and we're going to get y squared. So we're going to get y squared is equal to e to the negative x squared. Now we can take the square root of both sides, and you can say, well, look, y squared is equal to this, so y could be equal to the plus or minus square root of e to the negative x squared, But they gave us an initial condition where y is actually positive. So we're finding the particular solution that goes through this point. That means y is going to be the positive square root. If this was the point 0, -1, then we would say y is the negative square root. But we know that y is the positive square root. It's the principal root right over there. So let me do that a little bit neater. So we can get rid of, whoops, I was writing in black. So we can get rid of this right over here. we're only going to be dealing with the positive square root, or we could write y is equal to e to the negative x squared to the 1/2 power, and that of course is equal to e to the negative x squared over 2. So this right over here is, or y equals e to the negative x squared over 2 is a particular solution that satisfies the initial conditions to this original differential equation. So just like that, because we were able to, just as a review, because this differential equation was set up in a way, or because we could algebraically separate the y's dy's from the x's dx's, we're able to just separate them out algebraically, integrate both sides, and use the information given in the initial condition to find the particular solution.
Seems easy enough. Can you see that? Sorry, I can't really see, but
Yep, looks right to me.
okay. Awesome. Do you want to just, let's do like the first 4 and then we can just compare answers. Is that okay?
Sounds great. Just let me know when you're done.
Okay, sounds good. Okay, I think I have mine when you're ready. No rush though.
I'm working on the very last one. Give me like 30
No.
more.
Yeah, you're good. You
All right, I think I'm ready.
Cool. I'll do the first one. I got y to the third equals, I guess I pulled up both.
Yep.
That's what I got for the first one.
Perfect.
Second.
Yep. Y squared equals x squared plus c.
Okay. Yeah, that's what I got. Is that what you got too as well?
Yep. What did you get for number 3?
So I got y, but I did e to x3 over 3 and then times
Okay. I'm not really able to see what that says. It just kind of like the exponent on the e. I'm just wanting to make sure that I got that.
It's 3 over 3.
Okay.
Because it's 2 and then you integrate it.
Okay.
So that x squared goes to the x third over 3, or 1/3. I did 1/3 x to the third, same thing. But then you take the natural log of it, and then that's where you get that e x third over 3 plus c. But that c
Okay. Yeah, the way I saw it for a second, I thought it was like e to the x to the 3 over 3 power.
No,
was
yeah, it's that whole thing is the power. Yeah.
Okay. That makes sense then. I was like, that 3 divided by 3 is 1.
You're like, that doesn't make any sense.
Okay, we're good.
All right. Oh, word problems. I don't like word problems.
There's like 4 of them too.
Oh my goodness. Okay. Do we want to do these one at a time instead of?
Whatever you want to do, but I mean, that probably would be best.
Yeah, let's do these ones like as we go. Okay. So number 4, which really should be number 5 because there's 4 of the other one. think I got an answer, but I don't think it's right. Oh, just kidding. I see what I did. Never mind.
Do you need a little longer?
No, I didn't add an extra 0 on the K.
Oh, okay.
So I got 7.35, but I just redid it and I got 75.5825.
Yep.
Check that. Cool. All right. So for the rate of decay, isn't that y equals e to the kt or kt?
Yeah. There's another equation that's used in biology that's easier, but this works too.
Oh, what one do you use?
We use different variables too, but it's like NO minus N final to the ln to time, I believe,
Oh, okay.
because ln2 is half-life.
That's right.
But that's the half-life stuff, which this is kind of you're sort of finding the half-life here.
Yeah.
Or yeah, it's negative ln2, which, yeah, that would be this.
I'm ready when you are on that one.
All right. I got negative 0.0242.
Perfect.
Cool.
All right, number 6. I like these ones because they're easy. They look complicated, but the setup is nice.
Yeah.
Have an answer when you do.
All right.
Perfect. To 24,198.
Mm-hmm.
Okay, the last one.
I have an answer, but I'm not confident in it.
You get 32 days.
I like 31.508 or something like that.
Oh, I rounded up, but yeah, I did get 31.5.
Okay. That's not so bad then.
Yeah, you were right. 31.5 days.
Cool.
Awesome. That was the last of it.
Oh, nice.
Cool. That wasn't too bad.
Mm-mm. It looked a lot worse than it was.
Yeah. Usually when it's word problems, I'm like, oh, crap.
Yeah.
But that wasn't too bad. Awesome. All right. So I will post the link to the video, and then I guess this is the last time we'll talk.
Well, sounds great. Thank you so much.
Yeah, you've been awesome. Thank you. Good luck with everything.
Hey, same to you. Good luck on the final, and thanks so much for getting the video put together.
Yeah, not a problem. I'm sorry your internet was not being fun. But thank you for starting it.
I tried.
Yeah, you're awesome. Worked out pretty.
I'll just send both and be like, can we get extra points since we had 2 videos?
Yeah, exactly. Extra credit, right? 10 points of extra credit.
I think that sounds about right.
Yeah, I feel like that's a good idea.
Okay, well,
All
thank you so much. Like I
right,
said,
thank
good luck
you.
on the final.
right, you too. Thanks, Mary.
Bye.